And finally, let's focus on stereoisomers. And there are going to be two types for us, geometric and optical. So for geometric isomers to occur, that's going to happen when atoms or groups can either be arranged on the same side or opposite side of the compound relative to the central metal ion. And there's two things that will help us to distinguish whether or not it's cis or trans. First is going to be coordination number. So we're dealing with mainly coordination numbers of 4, which we see here, and it's always going to be that square planar geometry, or coordination numbers of 6, which is going to give us that octahedral geometry. Also, we must be dealing with ligand groups, okay, that are identical. So we have to have at least 2, mainly it's just going to be 2, ligand groups that are identical. So when we're looking at this square planar geometry, for example, here, we have 2 ligand groups here that are the same, and these 2 ligand groups here. And then for octahedral, we have this plane here, and then we have these 2 ligand groups that are the same. And on this plane here, we have these 2 ligand groups that are the same. So we have to make sure that we're dealing with coordination numbers of 4 or 6, and we have those 2 ligands that are identical. Now let's go ahead and talk about these structures. So in square planar, we're talking about around a plane, right? And so the plane is going to be flat, as we see here. And so when we have something that's going to be cis geometry, these 2 identical ligands are going to be on the same side. That's where the cis comes from. And then when we have those identical ligands across from one another in that same plane for square planar, that is going to be trans. And so this is how we actually get these cis or trans isomers based on where these identical ligand groups are arranged. Now with octahedral, the plane here is going to be vertical, you see, and then we have our plane across here. Again, when we have identical ligands on the same side, it's going to be cis. And when those identical ligands are across from one another on the same plane, it's going to be trans, okay? So you can use this schematic and understanding for studying compounds and making sure you make these clear distinctions and as many classifications as you can. Of course, this is all about you stopping and taking a flashcard moment. Write something small on the front and back about geometric stereoisomers. Get an example and detail down. So let's go ahead and do an example for ourselves. Which of the following compounds can exhibit cis-trans isomerism? So first, let's go ahead and gather our information about cis and trans. We know that we have to have things that have coordination number of 4 or 6, and we know we have to have 2 identical ligands. So with the approach for this question, we just want to go through each compound and make sure that it has 4 or 6 coordination number and 2 identical ligands. So let's go ahead and start that. Okay, so for this one we have nickel, and unfortunately we only have 6 of the same ligand, so we definitely can get rid of that. Not 4 or 6. Next, we have our iron, and we do have 2 different ligands, but there's only one of this O-N-O attachment. So we need 2 identical ligands here. Yes, we do have the coordination number of 6, but it won't work. Also, we have our chromium attached to the CO and NH3, and they're both going to be the identical amount, and we only need 2 identical ligands, okay? And then here we have our copper attached to CO, and there's 5 of them. Yes, we have 2 ligands, but we're going to need more than just this one single one. And so we cannot use that one either. By process of elimination, of course, A is the correct answer. Let's see why. Well, first, we have our coordination number of 4 and then 2. So that means we have a coordination number of 6. And we also have bromine here. And this bromine is going to be constituting our 2 identical ligands. So that's the reason why A would be our choice. Again, sometimes it's about recognition, and sometimes it's just about looking at compounds and saying, can this actually exhibit cis-trans isomerism? That's really how you want to approach these questions. Next, we have optical isomers, or enantiomers. And this is going to be coordination compounds that are mirror image arrangements of ligands in a chiral environment. And it must be non-superimposable structures that are considered optically active. So what is optically active, okay? An optically active substance are those that can rotate the plane of polarized light, mainly to the left or right. So that means you have a substance that is optically active. It can be a solution, and you add a ray of light through it. It can actually polarize that light or bend the light to the left or right, okay? All based on the arrangements that you see in these stereoisomers. So there's going to be many drugs and molecules that are used in pharmaceuticals that actually use these chiral and optic isomers that can really affect their biological activity. So of course we can use that for research science of the WUCA. Now one example will be like ibuprofen. They have optical isomers, one that's going to aid in pain relief and also one that's for side effects as well. So imagine this is having that same medicine that's going in your body and breaking down and doing two different things, all because of the isomers that are within it. So let's break this all down, okay? What we're going to usually start with is an octahedral complex. Okay, so octahedral means that's going to have 6 different ligands or 6 different things attaching to that central metal. So as you can see here, we have the complex of Cr, En2, Br+. And so what you would need to do is go ahead and figure out and calculate how much of each of these are going to be contributing to the coordination number for our chromium. That's actually going to be a Br2 here in plus. So you have our chromium, and then we're going to have our ethylene diamine ligand, which we know is bidentate. So there's 2 of them. So 2 times 2 is going to give us 4, and then 2 bromines. So that gives us 6 things surrounding that chromium. And so when we actually have our overall octahedral complex, we'll have our Cr here, and then we'll have that plane here, and then of course the vertical axis here as well. Now with our ethylene diamine or our En, it's bidentate, so the donor atoms are going to be these 2 nitrogens here, and that means that they're also going to make a kind of loop with one another, which again, when it comes to bidentate or things that are polydent, they can create those ring structures. So you will see a line going from this nitrogen to the other one, and they always have to stay that way. So that means whenever you rewrite something, you have to make sure that you are connecting this nitrogen to that nitrogen, no matter how much it moves around. So our goal is to take this octahedral complex and ask ourselves one question. Does it have an enantiomer or optical isomer? So how do we do that? Well, we need 3 things. 1, we're going to need the mirror image. 2, we're going to need that mirror image needs to be non-superimposable. And then 3, it must be hybrid. Okay, folks? So those are the 3 things we need to figure out if this complex has a stereoisomer. So what do? Well, let's go ahead and break down each part. First, let's get our mirror image. Now, technically, since there's going to be 3 things for me to do, I need to make sure that I'm going to have 3 different structures. The first structure is going to be my mirror image, and then I'm going to have to take that same mirror image and rotate it by 180 degrees to figure out if it's non-superimposable. And then once I have that overall compound, I'm going to compare it to my original compound to figure out if things are chiral. Okay, folks? So first, let's get our mirror image. So I'm just going to draw a line to dictate that this is going to be a mirror. Let's pretend that this molecule is looking in the mirror. And so let's say it's right here and it's looking through the mirror. Let me go ahead and rewrite that better. Apologies. So let's just say we have its eye right here and it's kind of looking in the mirror this way. So that means you can kind of orient this as left and orient this as right. If it's looking in the mirror, you're going to have the same structure. Let's go ahead and write it. You're going to have your Cr. These vertical bonds are going to stay the same. And then you're going to have one bond going in the back of the page this way, another bond going to the back of the page, and then one bond coming out and one bond coming out. So as you can see, I kind of just wrote the schematic of the octahedral shape of this overall molecule. Now, when it comes to figuring out what would be in the mirror image, anything that's in the front is still going to be in the front. So this bromine is here, and when you look in the mirror image, you kind of face the mirror portion, and that bromine is also going to be here. This bromine is also going to be here, so you see they're in the front. Anything that's in the back is going to stay in the back. So this nitrogen here is going to stay in the back, this nitrogen here is going to stay in the back. And again, because these nitrogens are connected to one another, they also must be connected to one another in the mirror image. So we now have our mirror image. Cool. That's always going to be our first step. Go ahead and get that mirror image. Next, we must verify if this mirror image is non-superimposable. So how do we do that? We take basically this axis here with the chromium here, and we're going to rotate our ligands by 180 degrees. Another way to write that is going to simply just put our vertical axis, and then we're going to rotate it 180 degrees. And that means every single ligand here is going to be rotated by 180 degrees. So what do we need to do? We need to first set up our new compound here. Chromium, our vertical attachments are going to stay the same. And then we're going to have 2 attachments going to the back of the page, 2 coming out the front of the page. And now we need to do our rotations. So when you're looking for the non-superimposable image, this is probably the hardest part because we need to rotate each and every ligand, and every time we make a rotation, we need to make sure we are verifying that rotation on the brand new molecule. So because we have some of the same ligands here, we can label this as ligand A and this one as ligand B. And all we're going to do is basically, again, move each of these ligands in 180 direction. So for this bromine here is now going to move over here. Okay, so it's going from here and it's doing a 180 and moved over here. That means we now have bromine A over here. Let me get a better mark. Okay. Now we have bromine A over there. And I'm going to be erasing it each time just so that we are on the same page and there's no extra confusion here because yes, we are moving ligand by ligand. So again, we're going to have bromine, this bromine moving 180, which is going to be now in this orientation. So we have a bromine here. Next, we're going to take this bromine and move it into this orientation. Again, 180. So again, it's going from this orientation now to over here. So both our bromines are now in two different orientations here. Next, we're going to have our nitrogen here go into a 180. So let me get a different color. Let me go ahead and erase the previous attachments. So now we're going to have this nitrogen here move 180. So it's going to now be in this attachment. Now, because this nitrogen is attached to this top nitrogen here, we still have to make sure rewrite that attachment there. So even though it may look weird, now this nitrogen is in the front and it must be forced to attach to the nitrogen that is in the upper plane here in the vertical part, just to verify that we're keeping everything the same. All right, let's move forward. We now have this nitrogen that we're going to move to 180. So this nitrogen is now going to move over here, 180. And now we have this nitrogen here. Let's go ahead and get a different color. Let me erase those. Boom, boom. Now we're going to have our final nitrogen that we already moved here, okay, which was this one here. And we have moved it over here to this one. But remember, the connection still has to be connected to the nitrogen down here in the bottom. So I'm just going to make sure that I make a connection to this nitrogen. Okay, we have effectively rotated our mirror image. And now this is the compound we get. Now we need to verify if it's non-superimposable. So that means I can take this compound and layer it to our original compound here. And if they're equal to one another, then they're seen as superimposable. So there will not be optical isomers. But if the connections are different, then they are optical isomers because they're non-superimposable. So as you can see here, the bromines are the same. So bromine, the bromines are the same for both of them. But the connection here, this nitrogen is connected now to nitrogen in the front. So this yellow connection to the nitrogens have changed, and this pink connection to those nitrogens have changed as well. So because of that, this structure is not superimposable for this structure, so they are definitely optically active. We now have our mirror image, and we know they're non-superimposable. Now the final thing we have to ask is it chiral? That's how we're going to verify it. Is it chiral? And so to answer this question of is it chiral, we have to understand what it means for these compounds to be in chiral environments. So a chiral environment is basically an environment where it matters if you have a chiral molecule or if asymmetry exists. So think of like a baseball glove, okay? There's specific gloves for the right and the left hand. And those can be considered as chiral environments because there are only specific hands that can fit into each glove. So that means once you have that non-superimposable mirror images, we have to make sure that they're also asymmetrical. So if I'm looking at this image here, now to write like a line going through it, you would see that either side are not equal. So when both sides are not the same, they're going to be seen as asymmetrical. That asymmetry is going to help us realize that we're dealing with something that is chiral. You also will see the other optical isomer or enantiomer here is also asymmetrical. Now, if you do see things that are symmetrical, we know that it cannot be an optical isomer. If you see things that are superimposable and can layer onto one another, equal to look the same, we know it's not an optical isomer. Okay, folks? So you just want to keep that in mind as we're going along. And so because of this, because they're asymmetrical, because they're non-superimposable, when they're in chiral environments like the substance and the plane of light going through the optically active substance, of course, they're going to display different properties. Okay, folks? And so you can change the different chiral environments. It doesn't have to just be about a plane of polarized light, but that's going to be our focus for our class. So again, if you just want to quickly spot if something is chiral, just look at the symmetry. Because you can actually write a plane going down this molecule and either side looks different, you know they're not symmetrical. They have to be asymmetrical. Okay? So symmetry is going to be our signal for if the molecule is going to be chiral, because sometimes we're not really focused on the specific environment it's in. All right. So we basically have proven that we have optical isomers because we have a mirror image, we have a non-superimposable once it's rotated and all the ligands are changed and moved around, and we know it's chiral or asymmetric. Let's go on to our last example. Okay, let's take what we learned to another example, like which is a pair of optical isomers here. So it says, consider the following octahedral complex structure, each involving ethylene diamine and two different unidente ligands. So uni is going to be the same as our monodente ligands as well. Okay, folks? And this question asks, which, if any, of the following is a pair of optical isomers? So for optical isomers, we know that we have to have that mirror image. That is going to be non-superimposable. And we know things have to be chiral or asymmetric. So what we can do is go ahead and look at our answer choices. We have A through D, and then we have none of these choices are correct. We have to make sure that we can prove every single answer when you see this kind of none of these choices are correct. Sometimes people could just be like, oh, I found an answer, let's move on and answer. But you always want to ask yourself, wait a minute, let me prove that I have this answer correct, because what if it is letter E, for example? Okay, folks? So just by looking at these complexes, we can start asking certain questions. Like, for example, which ones are chiral? That means which ones are asymmetric. That can help us kind of get rid of certain things. So we can see that these are symmetrical. They're kind of the same on either side. And this one's also symmetrical. So no matter what, they cannot be optical isomers. So that means anything that has 3 and 4, we can get rid of. Now for letter D, it says that we're comparing structures 3 and 4, and we want to know if these are optical isomers. As you can see, they're the same thing. So there definitely wouldn't be optical isomers here because they can be layered. So they're superimposable mirror images, and they are not chiral. Next, let's look at 1 and 4. Let me go ahead and erase this and to go ahead and compare number 1 and 4. They are not the same isomers because they both are not chiral. So you need to make sure they're chiral. Again, this one's not chiral, this one's not chiral. So I'm just going to get rid of anything that has 1 or 3 and 4 in it, because we know that they're not chiral because they're not asymmetrical. Now, finally, we're down to letters A and letter E. And a lot of times people will say, well, I'm just going to answer it, and the answer is letter A. But we have to make sure we can prove that the answer is letter A. So let's go ahead and look at these structures. First, are they chiral? Yes. So that's a good thing. How else can we go ahead and look at them? Are they mirror images? Well, one thing you can do is take your first structure and just write the mirror image of it. So I'm going to take my metal here. It's attached to nitrogen here in a Y. It's attached to nitrogen here. It's attached to an X here. It's attached to nitrogen here. And it is attached to another nitrogen here. These are going to be our bidente ligands. Now I'm going to do the mirror image. So I'm going to have my metal as well. Our nitrogen and our Y groups are going to stay the same. All right, and as you can see, we're just going to create the mirror image. So if I'm looking at it this way, I'm going to have my nitrogen and my X value, or my X ligand in the front. Let me go ahead and write that. I'm going to have nitrogen here and X here. Okay, folks? And so this nitrogen is attached to this nitrogen. So we're going to go ahead and make that attachment. We also have these two nitrogens back here that are going to be the same. So as you can see, structure 1 and its mirror image is actually structure number 2. So structure number 2 is the mirror image of it. So that means we have things that are chiral, and it's the mirror image. Now the final thing we need to do is rotate it 180 degrees to verify that it's going to be non-superimposable. So let's go ahead and do that. Okay, so we're going to rewrite our metal here. And as you can see, we're going to move everything about 180. So this N is now going to be over here. Okay, that means it's still attached to this nitrogen up here. So we already consolidated that one. This X is now going to be back here. Okay, so we already got that ligand. This nitrogen is now going to be over here where this X is, okay? And then this nitrogen is now going to be over here where this X is. So I'm writing X instead of. Okay, so now the big question is, are they superimposable or are they non-superimposable? If I take this structure and I take structure number 1, I see that there are difference in those connections, right? Even the ethylene dienes, the ethylene diene bioidentical ligands here, they have different attachments and different arrangements. And so that means that, yes, they are non-superimposable. If you were layering them on top of one another, they would not equal. So because they're non-superimposable, they're chiral, and we have a mirror image, our answer would be letter A. And that's how we kind of combine all this together. Okay, folks? So the coordination challenge for our transition metals is over, and they all came out on top with fierce coordination compounds created. So we got to learn about these coordination compounds and what structure they can create. And then the next part, we're going to focus on describing bonding in these complex ions with valence bond theory and hybridization, and then use crystal field theory to explain the properties of complex ions like color and magnitude. See you there for our next challenge, folks.